Hello everyone and welcome to the 13th lecture of the course Advanced Structural Analysis. We have briefly started some of the example problems on the general stiffness analysis, and with this session we will try to extend these problems to the frame structures. We will try to see the general conditions of the equilibrium which need to be defined for the frame structures. We will also talk about the frames which are available with the sway condition and without the sway conditions, and then finally we also identify the post computation steps of the given system. Now, as we continue with the discussions which we were having in the last session, we came up with the idea that if the member loads are distributed in the given system, we can have the contributions of the member load in the part of the second component, which is the member load contribution or the fixed end reactions of the given system, and corresponding to that we can now describe the given set of equation by the same format, which identifies P is equal to P L plus S into delta for the given problem. P of L typically, if the member loads are not provided, will be 0, because that will not contribute to any amount of the fixed end reactions appearing in the ends of the given system. And in cases where the member loads are provided, corresponding to the given identified member loads, we calculate the fixed end reactions of the system, and then in the directions of the identified degrees of freedom, which were the theta b and theta c in the original problem, we evaluate their values. Now, as a next step, once we have evaluated the theta b and theta c in the given problem, we move to do the post computations of the given system. As the same case of the discussions related to the simple problem with the joint cases, we identify that the member forces and the reactions of the system can be described in the similar manner, where A of M L component defines the amount of the member forces with respect to the fixed ended system part. Similarly, A of R L defines the amount of the reactions appearing at the respective directions of the reactions with respect to the fixed ended system, and the S of M components for both the system, we can define this S of M with respect to the given system of the member part, whereas this can be defined as the S of M or S of R for the given system, which means that this is corresponding to the reactions of the given system. The delta value has already been evaluated in the previous step. So, now by knowing the values of the fixed end components and the respective stiffness contributions of the given system, one can easily evaluate the values of the overall member forces and the support reactions. Another important point which we can again bring is that in the previous part we have considered that the stiffness matrix is same as we defined originally in the given system. In the same manner, when we define the S of M and S of R, the system will be remaining same which we have defined initially for the given problem. So, in each of the cases we are considering the system to be a kinematically determinate system, and then we are releasing the first degree of freedom over here with the unit amount, and as the second case we are releasing the second degree of freedom over here as the unit case. And with these both the cases, even if we define the member loadings differently, these cases are going to remain same. We are not going to bring the amount of the loading on these cases. That is why the contributions of the stiffness matrix are not disturbed by any further changes in the loading profile of the given system. So, what S of M value and S of R value we have evaluated in the previous cases where the joint loads were only active, they will remain similar, only we need to update the values of A of R L and A of M L for the given system. So, if we now look at briefly the system of A of R L and A of M L, we understand that at the joint 1 we look for the reaction joint A, the reaction R 1. It is in the positive direction of the R 1. So, it happens to be positive 15. The second moment reaction, which is R 2, we define this value as 15, which is also in the anti-clockwise sense positive initially considered for the given system. So, this value will also be positive for the given system, and then we move to the third reaction, which is over here the R 3 value, again in the upward direction positive for the given system. So, we consider it to be 30 positive. We move to the fourth reaction R 4, again positive vertical in the given system, and that comes out as 15 positive in the given system. But at the same time we understand that there was an active joint load at the position of the C, which was having a load of 20 kilonewton unit also, and we include the contribution of that as well in this part, which is provided with respect to the minus of minus 20, because it is the contribution of the load. So, when it comes to the reaction we have to reverse its sign, that is why I have taken the first sign as negative, and then the second, its direction is downward, which is also negative as per the sign convention. So, we consider it minus with minus of 20. One can easily understand this as well, that as the load is downward, so amount of the reaction which it will contribute has to be provided in the upward direction. So, that is why one has to add the 15 plus 20, that will be giving us the net reaction in the direction of R4. In the similar manner, now we can move to identify the reactions with respect to the given system fixed ended part as well. The directions of the member forces are defined AM1, AM2, AM3 and AM4. Now, in order to define these forces, we will come back with the same idea which we initially defined, that these member force reactions or member force components will be having their directions and magnitude same as the reactions which are appearing at the fixed end supports which are nearest to these joints. So, if I look at the joint B, the reactions which I am going to get there is 30 in the upward direction and this moment of 7.5 in the clockwise direction. So, I understand that over here, due to the fixed ended system, the amount of the member end forces will also be appearing in the same direction, vertical as a shear and clockwise as a rotational moment of the given system. So, we define the values as 15, which is for the corresponding system. Now, one must understand that when I am calculating this value, it should be only calculated with the member AB, because this is the end action force of the member AB of the given system. The net value of the 30 which we are getting over here is the contribution of the load coming from the member BC as well as member AB of the given system. But if I take the contribution of only member AB, this net reaction over here is 15. So, 15 plus 15 which has been considered. So, the first contribution of 15 which is corresponding to the uniformly distributed load has been considered, which is 15 for the given system. Similarly, the moment contribution of the given system which at this joint appears to be 15 kilonewton meter. We consider the WL square upon 12 of the given system, which will appear same as this value in the clockwise direction at the given point, and we consider that this will be minus of 15 in the given system. Then we move to the second joint over here. We realize that at this joint the contributions are only with respect to the member BC. So, we will directly take the values which are available over here. The first value of the shear is 15, which is positive, and the second value of the moment is 7.5 in the clockwise direction, which is negative. So, knowing these values, now one can easily calculate the associated values of the net moment, net member reactions and the external support reactions of the given system. So, once we have these values associated with the given problem, we can easily evaluate the net post processing of the given system. So, the general idea of evaluating the support displacements with respect to the free degrees of freedom which we did, along with that we are also now able to evaluate the external support reactions and the internal member forces of the given system. So, this typically concludes the basic discussions on the post processing of the given system. Now, as we move ahead with the frame, we understand that in frames there could be two possibilities. One, that the frames which we are considering have been considered to be inextensible, that means members are not having the change of length in their systems allowed. If we consider the change of length in the given system, the relative degrees of freedom will significantly increase. So, if a general system of the analysis we consider that this is a frame, at this point we consider the degrees of freedom and the extension is possible for the given system, that member length can change. So, these are the three degrees of freedom which will be possible at both the ends. But if we say that member extension or the length change is not possible, member cannot move in the upward direction because the bottom one is fixed and that will lead to change of length of the column member. So, that is why we remove this reaction, this possibility of the deformation. Similarly, this vertical translation here will also be avoided. Now, when it comes to the horizontal movement, we understand that if this horizontal deformation and the second horizontal deformation remain independent, they will result into the net change in the length of this given member. So, the only possibility that this can be allowed is that out of these two, we have only one independent value, and that comes out as the general condition of the degrees of freedom in the given frame. We consider that this is this frame sway, which is the movement in the lateral direction. In cases where we just restrain the given system for any kind of a movement, the sway value will be restrained in the given system, and that is what we have considered in these cases which have only the rotational components, but no sway allowed in the given problem. So, all these problems where only the rotation component are provided or the degrees of freedom of the system are only with respect to the rotation, the evaluation of the equilibrium condition will be with respect to the moments. So, if we say that the given joint is with respect to O, which is defined over here, and with respect to that joint we have some possibility of rotation to take place. So, the net condition of the equilibrium will be defined as the moment at the point O will be equal to moment with respect to the member OA, moment with respect to the member OB, moment with respect to the member OC, and moment with respect to the member OD, if we have more subsequent members in the given system, they all be connected together. So, at a particular joint, the number of members which are connected, they all be contributing the net moment associated with that given particular point, and this is associated with the conditions where the degree of freedom is considered with respect to rotation. Now, we move to the second case in which we do not restrain the translations in the lateral directions, and in those cases, as the members are inextensible, at least one independent translation in the horizontal direction or in the sway direction could be possible. We have just shown few examples. Now, in these cases, we have a possibility of rotation to take place at this joint, we have a rotation to take place at this joint as well, but at the same time we have a possibility for the member to undergo a sway which is giving a common value of the delta at both of these ends of the given system. The same thing can be defined for the second member as well. Now, for these given conditions, when the members are considered with the sway, we typically identify that with respect to the sway, one has to identify the equilibrium of the forces in the direction of the sway, as sway happens to be a translation. So, the equilibrium will be defined with respect to the forces in the given direction. Now, we understand that if it comes to define the forces in the direction of delta, primarily those forces will be the shear forces which are coming from the vertical members, because we have already considered that members are inextensible. That means, this given member of, if I just label it say A, B and C of the given system, we understand that member AB is not going to change its length. So, there is no possibility that the force in the horizontal direction due to the axial deformation will be generated. The only possibility for the member to have a horizontal force or in the direction of the delta is the shear force due to the member BC of the given system. So, ideally when we define the conditions of the sway, we necessarily satisfy the conditions of the shear at the level of the given story at which the sway is being provided. We will see these in the subsequent cases of the example. Now, as a simple case, we have first considered a member frame which is having no possibility of the sway in it. One of the member load is applied on the span AB of the given system. The length of the member with respect to this part is defined as L, and the length of the second member BC is defined as H. Now, as a first criteria of the given system, as we have considered the given problem, we realize that it has three joints, joint A, joint B and joint C of the given system. As the joint A and C are fully restrained, we understand that there is only a possibility of deformations coming from the joint B in the given problem. Translations are not possible because the second end A and the end C of the given system for the given joint B are fixed. So, any of the translation in the given member will lead to the change of the length, and that is why the only possibility of the degree of freedom at the joint B is the rotation. So, we define that the rotation at the point B or theta B is the only possible degree of freedom which is available in the given system. And now, with respect to this, we define a kinematically determinate system in which we restrain all the degrees of freedom in the given problem, and this system appears like this. So, this is our kinematically determinate system in which we have restricted any of the degree of freedom to take place. Now, we will consider that the fixed end forces can be evaluated. So, with respect to the external load which is applied, we can calculate the fixed ended reactions. So, this value will come out as P by 2. Reaction over here will also be P by 2, which I can directly translate to this point. The net moment which will appear here will also be defined PL upon 8, and over here which is also PL upon 8 for the given system. We have taken these values from the standard results which we have generated in the force method. One can again go back to those discussions and get back these results for the standard fixed ended systems. So, once we have these values, we understand that as a next step of the analysis, we need to release the degree of freedom with respect to the allowed degree of freedom of the original system. So, we consider the given problem again in the same manner, and we release the one degree of freedom which is the rotation at the joint B. But one must understand that the joint B is the rigid joint. So, even if you release the rotation at the joint B, that does not mean the member AB and BC will have two different rotations of the given system, but we will simply say that the overall joint moves in a perfectly rigid manner, and this will be some amount of rotation which we have provided at the given system, which is common. Now, corresponding to that, we can draw the deflected shape of the given system, and with respect to this deflected shape, we can now evaluate the end moments in the given problem. We do this process to calculate the end moments, and once we have those values available with us, we can now write the standard condition that P is equal to PL plus S into delta in the given system. So, P of L will be evaluated with respect to the system 1, whereas S will be evaluated with respect to the system 2, where we have released the unit rotation in the position of theta b in the given system. So, once we do this calculation, we realize that this is what we initially generate. This is our loading system or the fixed ended system, and this is our system which is corresponding to the unit rotation released at the joint B of the given problem. And once we generate these set of values in this given problem, we understand that the P equal to P L plus K S delta can be defined. P is the amount of the force in the direction of the given degree of freedom. The degree of freedom we have defined over here as theta b. The force which we have defined over here is P L upon 8 as per the loading condition. So, we define this value as a P of L. The P value, which is the net equilibrium condition of the joint, as there is no moment active over here directly at this joint. So, this is 0. P of L with respect to the loading system we can define as P L upon 8. The direction of this is opposite to the theta b direction. So, it is negative, plus S, which is now only one single coefficient because we have only 1 degree of freedom. So, the net moment at this given point, which is 4 E I upon L plus 4 E I upon H in the given system, and this will be multiplied with the unknown value of theta b which we want to evaluate. This stiffness coefficient is positive because it is in the same direction as the original direction of the theta b which we have defined. Now, with this idea in mind, we define this condition, and by solving these values by the defined value of P, L and S expression in the given system, we can generate the theta value of the given problem. Once we have got the theta value, now we move to calculate the support reactions and the member end forces of the given system. We realize that the support reaction and the member end forces can again be decided in the same manner, that A of r will be equal to A of r with respect to the loading or the fixed ended system plus S of r into delta in the given problem. And similarly, the A of m, which are the member forces, can be defined as the member forces with respect to the fixed ended or the loading system plus S of m into delta in the given problem. Now, in order to evaluate the values of these loading components, we again consider the fixed ended system and we calculate the directions or the values of the reactions in the direction of R1, R2, R3, the 3 reactions over here, and the 3 reactions in the given system R5 to R6. Now, with respect to these values and the associated value of the member forces, we calculate the end forces of the given system. We have done the same system again. This is the loading parameter in which all the degrees of freedom are restrained. This is the first system in which theta b with the unit value is released in the given problem, and once we solve these parameters, we get the net value of A of r, which is defined in this manner. We get the net value of A of m with respect to loading, which is defined in this manner, and we also calculate the A of r with respect to the delta, which typically means that these are the contributions provided with respect to S of r and S of m in the given system. As we have only 1 degree of freedom, the S of m and S of r will actually be a single column vector of the given system. So, knowing these values in the given problem, one can easily evaluate the support reactions A of r and as well as the member end forces A of m in the given system. Now, as we move to the next case, we have a system in which there is a possibility of the sway as well. So, when we look at this problem, we have a joint B where we have a possibility of the rotation theta b. We have a joint C where also we can define the rotation theta c, and then we have a joint C where there is a possibility of the given member span BC to undergo sway in the given direction of the lateral movement. Now, in these cases, we have considered that the rotations of theta b and theta c can be accommodated by the simple moment equations, whereas now we need to identify the conditions of the equilibrium with respect to the sway parameter of the given system. So, to start with this part, we identify first the given system with respect to the same condition that all the degrees of freedom are restrained in the given problem. So, as we have initially defined, we restrain both of these supports of the given problem. As we restrain the given supports, we understand that corresponding to the given loads which have been identified in the given problem, we can now calculate the end reactions of the given system. Now, in order to define these end reactions, what one can easily do, we can calculate these values over here, that with respect to the 100, which is the amount of the force over here, I can consider the given system in this manner as a simple fixed ended member, and I can calculate that there is a load which is active at one position 4 meter from the left and 6 meter from the right side of the given loading on the system. Now, one can go back to the same discussions which we did in the standard force method, that corresponding to a fixed ended support or the fixed ended beam if there is a concentrated load active at any point of the given system, we can evaluate the end moments of the given system for these cases. So, using this idea, we evaluate the end moments of the given problem. We realize that these end moments, typically if I define this value as A for the given system and this value as B for the given problem, and this load parameter being P, we can understand that the given moment values come out as P A square L, sorry, A square B, which is at this end, upon L square, and over here it comes out as P A square B upon L square for the given system. As we have calculated the values of these end moments of the given system, we can also calculate that these values will not be giving us the same amount of moment, which typically happens with the point of the loading if it is centrally placed. So, now with respect to this net moment imbalance, we need to also generate the support reactions which will be available at the two ends of the given system, and these support reactions will be added over and above the actual reaction which is provided by this given system as a simple fixed pin jointed part of the given problem. So, if we consider a system like this in which a given member load of 10 units is provided at the beam having a span length on one of the side 4 and another side 6, we can evaluate the two reactions of the given system. These two reactions will typically be evaluated as the 10 into 6 upon 10, which is the total length of the given member, 10 into 4, which is the second part of the length, divided by overall length of the given system, which is 10. Now, these are the reactions which are typically provided for a pin jointed system, but once we have a fixed ended system like this, we have evaluated the end moments, and along with these end moments, the imbalance amount of the reaction also need to be added in these parts to define the net reaction of the given system. So, with this idea in mind, we will try to calculate the end reactions in each of these systems which we have identified. This will be our first system which we define as a fixed ended system of the given problem. As a next case, we come up with the similar problem and we consider that for the same problem we will release the first degree of freedom, which is the theta b in the given problem. So, as we release the theta b in the given system, we have this joint which will undergo the rigid rotation of the amount theta b, the common value of theta b for both the members, and corresponding to that we can define now the deformed shape of the given system, at which we will be able to generate the deformed the fixed end moments of the given system. As a next case, we will consider the amount of the rotation to be released at the joint C of the given problem, and corresponding to that again the user can define the end moments of the given problem. And finally, as a third case, we can release the amount of the translation or the sway in the given problem, and once we release the rotation or the translation in this part, we will be able to generate the given system with respect to the standard idea of the end reactions of the given problem. So, this will be our system 1, which is corresponding to the fixed ended part, and this will be our system 2 with respect to the rotation theta b. This will be our system 3, which is with respect to the unit rotation theta c being applied here, and this will be our system 4, which is with respect to the amount of the translation or the sway provided in the given problem. Once we are able to identify these individual systems with their reactions, we can again go ahead with the calculations of the net equations that P is equal to P of L plus S into delta in the given problem. As in the given problem, we have 3 degrees of freedom. So, we realize that these equilibrium conditions with respect to the joint B will become as the moment at the point B. With respect to the joint C rotation, it will become moment at the joint C, and with respect to the sway, it will become the force in the direction of the member BC or force in the direction of delta with respect to the member BC in the given system. So, using these 3 conditions of the equilibrium, we will be able to identify the overall conditions of the equilibrium for the given problem. Now, as we move ahead, we come up with the first case, we identify the given system, we fixed all the restraints of the given system, and once we do it, we identify the fixed ended reactions in the given problem. We identify that these are the fixed ended reactions for the given member AB. One of the value is 144, another is 96, as these are having imbalance or the net moment is available in the given system. So, with respect to the given loading, we also add the contribution of the net imbalance moment, which will be balancing the couple of the given problem. In the same case, we can evaluate these values for the second member and the third member of the given system. One can directly go back to the standard of these results, which are given in most of the reference books, and they typically identify these end reactions of the given system also with the net values, and that can be directly referred. In most of the computations, when we do the real scale problems, we have these values or these standard tables available with us. So, that is where the intention or the focus should be to understand the basics of knowing these parameters rather than remembering these answers. So, once one is able to calculate these parameters of the given system, we generate a given system which is the fixed ended system of the given problem. And now, as per the original problem, I will just try to define the idea of the moment in the direction of the due to the fixed ended part. I will also define the moment at the point C due to the fixed ended part, and I will also try to define the corresponding force in the horizontal direction due to the fixed ended part in the given system. And as we try to look for these three values, I define that at the joint B, the net moment value is appearing as 106, which is in the same direction as the original theta B, which has been considered anti-clockwise positive. So, m of B comes out as 106. In the same manner, the moment at the joint C of the given system has been evaluated, which comes out net as 226, opposite to the anti-clockwise direction. So, it is minus of 226, and the net force in the horizontal direction in the positive x direction of the given system is evaluated, which comes out as 17.6 minus 64.8 in the given problem. So, with this idea, we have evaluated the contributions of the fixed ended forces for the given problem in the directions of the 3 degrees of freedom which we have defined in the given problem. Now, we will do the similar problem for individual set of release of the reactions, release of the degrees of freedom in the given problem. So, as we go ahead with the first degree of freedom, which is delta 1 or theta b in the given problem, we release the rotations over here and we describe that the deformed shape will be appearing like this. In each of the cases, as this is the member which is subjected to the rotation theta b, we define that this is having 4 EI theta b upon L, the amount of the moment. Over here, this is 2 EI theta b upon L. The EI value for these given members as 4 EI, so accordingly the contributions have been taken. Similarly, when it comes to the member BC, the contribution is added with respect to the 4 EI upon L for the given member. Again, for this EI value is considered as 4 EI, so we have added the contribution of same margin in the given problem. So, by using these all criterias and by calculating these values, one can easily evaluate the contributions in the direction of the joint B, joint C, and the delta or the force contribution with respect to the delta of the given system. So, we are now looking for these three contributions with respect to the theta b contribution of the given system. So, as I go to the joint B, I realize that the net value of the moment over here is 4 into 4 EI upon L1, which is corresponding to the first joint. Secondly, it is corresponding to the second, which is 4 into 4 EI upon L2 for the second member. I realize that the L1 and L2 both the values happens to be 10 meters. So, I will add this contribution as 32 EI upon 10 for the given problem. So, this happens to be the net summation of this amount of this first moment and the second moment, which are the net moment at the joint B of the given problem. Similarly, I go to the joint C and define the moment condition over there, which appears as 8 EI upon L2, and that can be defined as 8 EI upon 10 in the given problem. Finally, we define the net horizontal force in the given system. For that, again we have to define that are there any shear forces appearing with respect to the member CD and member BA in the given problem. Member CD is not undergoing any deformation, so there is no shear force coming from it, and member BC or member BA will be having amount of shear force which is active at this position, and that has been evaluated as 6 into 4 EI upon L1 square, and we just define this value as 24 EI upon 100 for the given system. So, once we have these values, we evaluate that these values are the contributions with respect to theta b parameter in the given problem. I do further similar condition with respect to the rotation theta c in the given problem. We again evaluate the values. We do the similar contribution with respect to delta being provided in the given system, and we evaluate the same contributions. Once we sum up all these parameters together, we realize that these are the first set of contributions which are added with respect to theta 1 or the theta b components of the given system. These are with respect to delta 2 or the theta c component of the given system, and these are with respect to delta 3 or the actual sway delta of the given system. So, these three values which have been added over here are the contributions in the directions of moment at the point B, moment at the point C, and the net shear in the direction of the given member BC or the delta direction, and these are contributed by individual theta B, theta C and delta components of the given system. Once we have these values, we can evaluate the standard values of the delta 1, delta 2 and delta 3 in the given problem. Knowing these values, one can now easily move ahead and try to define the condition of equilibrium also. So, this condition of the equilibrium, while defining it, we have gone back to the given problem and we have realized that at the basic starting problem, we had one force which is active in the given direction, the horizontal direction. There was a force active at the given system. So, other than the concentrated forces, there was one load of 80 kilonewton which was active in this direction. There was no direct moment active here, there was no direct moment active at this joint. So, we have considered that the moment with respect to m of B and m of C both are 0, and only with respect to the delta direction we have a net amount of force which is of 80 kilonewton. In the similar manner, we can also now go ahead with the calculations of the support reactions and the member end forces. We are not showing this over here, but by looking at these three systems cumulatively as well as the loading system of the given problem, one can easily define these values which can be calculated as the overall analysis of the given system. So, what we understand that for rigid joint frame structures, the equations corresponding to the rotation can be defined for the each of the unrestrained joint or the joints where the degrees of freedom are available. In the case of any of the Schweitzer being possible in the given problems, we also define the equilibrium condition in terms of the sway parameters of the given system, and typically while defining the sway, we take care that the member extension, as these are not being allowed. So, these will only be contributed by the shear forces of the given members, the cross members of the given system. And finally, to calculate the support reactions and the internal member forces, doing a parallel computation at the same time while we are evaluating the fixed ended system or the released in kinematically determinate systems, we can easily evaluate the overall response of the given system. With this, we stop over here. Thank you everyone.